Yeah, so first I just wanted to take a poll of like, uh, should I continue on expectation maximization algorithm, or should I just as mentioned on Discord, I should just go through maths that's not related to what was covered in the earlier lecture.
It, I think probably like it would be better to like just give a brief overview, like once go through a bit of material, bit of recap, and then probably we can start with the new material. I think it's been like 2 weeks sort of like to
Yeah,
catch up with that. So
yeah, okay. Um, so yeah, so first I'll just give a recap of what was covered in previous sessions. So in the first 2 to 3 sessions, we were mainly concerned about this maximum likelihood estimate, maximum a posteriori, and this full Bayesian inference. And then in last session, which last test session, we started about latent variable models. We saw a brief overview of GMM, and then in the last session, we started with uh, EM algorithm. So in EM algorithm, what we are trying to figure out is mainly the log likelihood, and by introducing some latent variables in the model. But at the end, we are still interested in log likelihood. Then we started initially with just saw fundamentals of Jensen's inequality, which we'll be using for proving the EM algorithm. So if you remember, this was the Jensen's inequality. The function of expectation is greater than expectation of the function, but conditioned on f is a concave function. And then we saw how that relates to uh, ensuring KL divergence is always positive. Then we started how to use Jensen's inequality to figure out the log likelihood that we are interested in. But here, the thing that is different from previous MLE estimate, likelihood estimate, is our XI is conditioned on some latent variables, and we are trying to figure out that latent variable as well. So yeah, so this is just marginalization, and then we saw why uh, without introducing a lower bound, why this would be a quite difficult problem, because we'll be trying to estimate a summation of log of summation, and it would be better if we can switch the inner summation and log. So that's why we then introduced the lower bound, and instead of a just single lower bound, we introduced a family of lower bounds so that it would be easy for us to handle those parameters and optimize for what we are interested in. So we saw, yeah, so and then we introduced this variation distribution Q. Like we had no idea, currently we don't have any physical interpretation of it. It's just a free parameter, if I say so, that we are allowed to nudge so that we can get a better estimate of a log like of our parameters that give us maximum likelihood. So yeah, and then just we multiply divided by this variation distribution Q, and then apply Jensen's inequality, and then we saw that we were able to switch the log term and summation, and now solving this is much easier than solving what we had previously. Then we also saw some intuition of how expectation maximization algorithm worked intuitively, what are different variation bounds, and how like iteratively optimizing over Q and iteratively optimizing over theta leads us to a local optimum of theta that gives us a good likelihood. So we are always interested in the parameters theta that gives us the maximum likelihood of a model. So yeah, and then we had this equation of evidence lower bound. uh, this was the equation, and then yeah, Q is as I said previously said, kind of free parameter, and in each step we maximize over Q, and in an M step we maximize over theta. In each step we think that theta is a constant, and in M step we think that Q is a constant. and then we iteratively keep doing it until we obtain we obtain a point where we cannot optimize further, and that's a local optimum. So this is essential thing in QNM step that we are interested in, and then we also saw a similar proof that was in like Bishop, but it's like you don't need to introduce Jensen's inequality, but you directly use the fact that KL divergence is always positive. But as we saw previously, even the fact that KL divergence is positive comes from using Jensen's inequality. And then and then we arrived at this equation that was like similar to exactly what we derived earlier. And so since KL divergence is always positive, the log likelihood is always an upper bound of our evidence lower bound, LQ theta. Yeah, so this was mainly what we covered in the last session. Any doubts? Is all of this clear? Because now what we will be going to do is like solve these two equations mainly. So if you have any doubt in this equation or this equation, then just let me know. This one and these two. Maybe you can give a thumbs up that if it's all clear, if we recollect everything, then we can go ahead.
Fenil, I had a small doubt. So in this case, like the theta is the actual model parameters, right? But we can't get there. Like basically, we can't find the optimal model parameter. We posit it to some distribution Q, and we try to get closer to the actual distribution by keeping in mind sort of staying nearer to the actual prior distribution in a way, right? Means
So
like let's say I'm not sure.
So it's like theta, yeah, theta, the model parameters that so theta, those parameters that you need to find that would maximize the likelihood of seeing your data. And this data is something that you already have, and you want to fit like you have some distribution P, and you want to fit those parameters, which would with those parameter settings, the probability of seeing your data is the maximum. So that's what theta is.
Okay.
And Q is your this variational distribution that you have introduced, so that a variational distribution over your latent variables P that you have introduced, so that you can get a family of lower bounds and then optimize over it, so that you can get to this local optimum of theta.
Okay. Got it.
Yeah, I think Josh is also here, and yeah, so what I was like just doing is was giving a simple overview of last time's session. So yeah, that was it. Let me know if you have any doubts.
Are we continuing with like last time's thing, or are we revising general stuff?
Yeah, so like people here are of the opinion that we should like I should give just a little brief overview, and then we can continue with this. But what I'm planning is like so I won't like I'll build up of on what like it's all up to you. So like I would just follow what you want me to do. Like if people want that I should continue, then that's fine. If we can also just do a separate math session that's unrelated to this. So I saw your comment on Discord that uh, we can continue. Sorry, we should do the math session, and even yeah, that's fine. But
Yeah,
yeah,
I don't mind anything. Uh, I am fine even if we continue with last time session.
no, but so the main thing is if you remember this and if you are comfortable with these two sets of equation, then only it makes sense for me to go further with it. Uh, Otherwise, yeah, I think a math session would be better. So, like, because otherwise we would be just like mainly focusing on just solving these two equations and or generally, yeah. So if you remember how these two equations came, and if people are comfortable with it, we can go ahead. Otherwise, let's not. So yeah, but people like just please say in the chat or anything, and I think we would just go with the majority. Okay, so I think that if we should just go ahead with the math session. Yeah, because mainly, if not today, I would have to cover it sometimes later. And it's better to just get those math fundamental out of the way. So yeah, but for the next session, please like go through the last session's lecture and yeah, and then let me know if you have any doubts. So in like the this wouldn't be like a 2 hour long session, hopefully. So the main two things that I wanted to cover is constraint optimization. The other thing was operations on functions. These are the two fundamental topics that I want to cover today. So for first constraint optimization, we always yeah solving a function of a vector x, and if we want to find the most optimal value of this function, then we know how to do it. It comes from multivariate calculus. We just uh, differentiate with respect to x and equate it to 0. So if a function is of x, y, z, then to find the optimal value, just solve these sets of equations. This thing is exactly the same. If this is a scalar quantity and this is a vector quantity, so if you differentiate a scalar with a vector, so you differentiate each component with it and you get another vector. So that's just some multivariate calculus. Differentiation of fx with respect to x vector is, let's x vector is x1, x2, x3. Then it just gives us this vector. Yeah. So differentiating a scalar with respect to a vector gives you another vector. And then we equate this to 0, 0, 0, and you get three sets of equation and you solve them. So, and here you don't have any constraints on like x, y, z that are the inputs of your function. They are free to go around anywhere. But in many a times you would find yourself in a situation where some constraint is given to you. So, for example, let's say f of x, y. So here my z vector is just constituting of x comma y is x square y. But now I have this constraint, which is x square plus y square is equals to 1. So now my x and y are only within those domain where this condition is met. I'm not like so. Otherwise, if I optimize it, then the maximum would just directly go to infinity. Like x goes to infinity and y goes to infinity. So, but now I can't choose the setting because infinity square plus infinity square won't give me one. So yeah, so the main technique to do this is add a Lagrange multiplier, and so yeah, so while doing this constant optimization, I don't know if you guys know this, that if gradient of any function is always like perpendicular to its contour, and if you know this, then that's awesome. But if you don't, I don't think I would go over that, because it's better if you would visualize it. And as I'd mentioned previously in our Discord channel, uh, a great place to learn multivariate calculus is from this Khan Academy YouTube's lecture. So it's taught by Grant Sanderson. So and all of this is kind of borrowed from there only. So just take a look. He has some nice visualizations that would like really nail it down. So, but yeah, we would kind of use the fact that at an optimum point, the gradient is always kind of perpendicular to the contour. So if I diagrammatically, what it means is, so this is x-axis, this is y-axis, this is the constraint. U curve is x squared plus y squared is equals and now what we need is so I'm just drawing contour lines of x square y. So it would be something like this. Yeah. So I hope you are familiar with contours are. So it's basically that this line corresponds to all those values where x square y gives the same value. Maybe it's like your f is 3 here, f is 2 here, f is 1 here, something like that. So for the f for f is 1, this won't be f is 1, f is 1 would be something like touching this, and this point would be 1 comma 1. So yeah, not really, sorry. But yeah, you get the idea. So uh, these are the contour lines, and what what so at the optimum point, what I mean is gradient is always perpendicular to the contour. So if so this is some line that I have. These are all the values of x and y that gives me my f value as 3, and the gradient along any of this point. So if I just take this point, so this would be kind of like the direction of my gradient around along that point. And yeah, and the other thing that you observe is it's kind of intuitive, but it's not mathematically rigorous. Again, for being for to ensure that it's mathematically correct, switch to that channel. But it's the optimum point will always be on the boundary of this constraint that you have and on the contour lines, because it's like as you move so yeah if so, mm, yeah, so if you have this contour, then you can always increase its value by moving up further away from the constraint. So this would be better, this would be better. at, at this point it would be it would be the maximum value that you can get. And if you move any further away from that, the value just even though it increases, but the constraint is not met. So the constraint yeah, so it's like you have this set of constraint, and you need to stay over this, and the maximum or minimum would always be at the boundary. So yeah, so and again, I know it's not mathematically rigorous why it's always needs to stay like be at the boundary of the constraint, but intuitively it makes sense that in one direction in one of the direction it would increase, and in other direction it would decrease. And as you if you want to increase, you just go in the direction that increases, and you can only go until you reach the boundary, because if you go any further, then the constraint is no longer met. So yeah, so we'll be using this fact two facts to get yeah to get our equation. And then so what I want to do is, let's zoom in further on this part, what happens here, well, at the boundary point. So this is our curve for the circle, and this is our contour that meets at the boundary point, and we know that this is the optimal point. And so at this point, these two contours meet here. So and the and so they both share this common tangent, and we know that at the contour, the gradient is always perpendicular to the contour. So the gradient of both of these functions point in the same direction. So they can be exactly in opposite direction, but it's like they point in the same direction, as in the vector direction. They always point towards the same direction. And so this is the main fact that we'll be using here, that the gradient of these two contours always point in the same direction. So now what we have is, let's say, so for the previous example only, we had f of xy is equals to x square y, and we have to maximize f of xy subject to x square plus y square is equals to 1. So what I would do is, this is, I'll just let x square plus y square minus 1 is equals to 0, and for g of x square plus y square minus 1. So it's maximize f of xy such that g of x is 0. So till here, does it make sense? Any doubts till here? Okay, moving further then. So we know, so the subtle change that we have made here is so x square y is kind of called a parametric surface, because yeah, so in one day it's always easier to visualize that it, it would be something, if I had just x square a one day surface, then I know uh, any quadratic function is just a simple parabola. But yeah, so the in 3D, if you try to visualize it would kind of give you a surface that has like contour lines, as I have shown here, for different values of x and y. And and this x square plus y square is equals to 1 is not a parametric surface. It's just a okay. It's just a curve that you have on a 3D space. So because it's similar to the subtle difference between, if I just give you a line x plus yeah, if I just give you a line 3x, this would be some 2D curve. But if I just give you some equation that x is equals to 9, so it's yeah, if you can draw the analogy between these two. So one of them is I'm just giving you this surface of x square plus y square minus 1, just gx. I'm not equating it to 0, so but I want this function. And this is just a parametric curve, g of x is equals to 0. And what I had so what we proved earlier is, not proved, but what we know for a fact is f of x and g of x. have the gradient in same direction at the optimal point. So this we showed earlier. And here again, g of x and f of x both are parametric surfaces. Here, none of them is a curve. So I hope you are able to distinguish between the two. And you have, if you have any doubts about parametric surfaces, curves, contours, and all of that, what they technically mean, again, that uh, multivariate calculus course would be a good point for you to start. So now, yeah, so we'll be using this main, yeah, so gradient of f of x, we know is along the same direction as the gradient of g of x. So I'm just using this some constant that denotes, so uh, it's in the same direction, but the magnitude can vary. So f of x can be pointing in I hat plus j hat, and gradient along f of x and gradient along g of x can be pointing to 3 I hat plus 3j hat. So the unit direction is always the same, but the scale can always vary. So yeah, so this is the major equation now that we have, uh, that gradient along, yeah, so gradient along f of x is the same as gradient along g of x up to a constant. So now we have this. So if we use our previous example, so it's kind of like this is a vector. I I think I just like z here. Remember z is a vector. So if z was x comma y, so we had f of z is equals to x square y. So the gradient of f of x y. This is just an example for 2D case. Along gradient of g of x y. And then yeah, this simply becomes for 2D case this vector. And yeah, we know how to solve this. This is just a differential calculus in 1D. So x is a scalar, f is a scalar. Yeah, everything is a scalar, and we can just do normal differentiation as we had done in higher school. And then this becomes del g of del x lambda times del g of del y. So now we see that okay, we have these two equations, but we have introduced this new variable lambda. And so we would have as many equations as there are dimensions. So like in so the dimension of z was 2, just x and y as scalars, and we got two equations. If z was x1, x2 to xn, then we would have get n equations. And but we have also introduced this additional lambda. So we are always like in a situation we are having n plus 1 variables, but just n equations. So we need one more equation to like yeah to solve all of this. So yeah, any idea from where we can get that equation?
Sorry, can you repeat the last part? Your audio got cut off.
Sorry.
Can you repeat the last part? Your audio got cut off.
Yeah. Okay. So yeah. So here, as I said, we are just equating the gradients, and the gradient vector like for an n-dimensional variable, if z was like x1, x2, x3 till xn, the gradient would give us n-dimensional vector, and we would equate it to another n-dimensional vector. So here n is just 2, then and we would get n sets of equations. But we introduce this additional parameter lambda as well. So now we have n plus one variable where n are the like the the n-dimensional optimal vector that we are interested in, and an additional parameter lambda. So it's like we have n plus one equations, sorry, n equations, but n plus one variables. So in order to solve this, we need one more equation, and like so any clue from where we can get that equation? I hope you understood that. But yeah, so for this, for x square y, for when g of x comma y is x square plus y square minus 1, so this would just become x 2x phi x square is equals to lambda times 2x lambda times 2. So if we are trying to solve this, then we know lambda is equals to y and x square is equals to 2 lambda y. So okay, now we have these two equations, but we won't be able to solve this because yeah, because there are three variables here. So how will we yeah, so yeah, my question is, what's the additional constraint that what's the additional equation that we can get? Let's go ahead and say it then. So here we forgot about the original constraint. Like we needed the original constraint to see that okay, at the optimal point both the gradients will point in the same direction, but we still need to ensure that okay, the x and y that we get after equating those gradients also meet the constraint, right? And so the third equation is kind of just like already given to us in the form of the constraint g of x is equals to 0. So all we need to do is like solve these two equations and more, and also equate g of x to 0. So the third equation that we have is x square g of x plus this. Now we have these three sets of equations, and we can just like yeah, we can solve it to find the optimal x, y, and lambda. So mainly we are here only interested in x comma y, but there can be situations where we are interested in this lambda parameter as well. So this lambda is called Lagrange multiplier, and so 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 now as we saw, we need to solve this uh, two equations. One is just a constraint, and the other comes from other is a set of n equations that comes from equating the two gradients. So compact way to write this, and this is called a Lagrangian, is so here this f of x is the original function that we needed to optimize. G of x is equals to c is the constraint, and this thing is called the Lagrange. And then we can just write so instead of optimizing f of x, if we optimize the so instead of optimizing f of x with a constraint g of x is equals to c, we can just directly optimize the Lagrangian freely over x and y. So if you see, so if we take the derivative of Lagrangian with respect to x vector, what we would get is and in free optimization we just equate after differentiating we equate it to 0, and then if I so as you saw, free optimization we would just equate each of these to 0. So we would equate the vector x with respect to 0, and then this would become 0, and this is nothing but the gradient of yeah, gradient of a function minus gradient lambda times gradient of a constraint. So if you see, then this directly gives us this first n set of equations that uh, we got here, equating the two gradients up to a constant. And yeah, so this Lagrangian is just like a compact way of writing it down, so that instead yeah, so that instead of doing a constant optimization, we are directly able to do a free optimization without any constraints. But the thing is, instead of doing it on on n dimensional vector x, we are kind of doing it on a n+1 dimension where you have this n-dimensional vector x and a Lagrange multiplier lambda. And if so, this is the like n-dimensional vector differentiation, and we also need to differentiate over the other variable that we have is lambda, and then this would directly give us the constraint because f of x is independent of lambda, so that would go to 0, and this would just give us minus lambda times g of x minus c. And then again, we would equate this to 0, and then we would be left with g of x is equals to c. So yeah, so like just writing this in the form of Lagrangian ensures that we can just directly do free optimization over this. So, and this is something that comes up in machine learning so many times. It's used in the proof of SVM mainly depends on this. We'll see later how even GMM uses this. Uh, the, even you can prove using Lagrange in the PCA. And so, yeah, so in, yeah, in many of the times machine learning, you will see this trick where you have to do some optimization given some constraints, and then you can incorporate those constraints and just do a free optimization over the Lagrange. And say you have multiple constraints, if you want to optimize for f of x, yeah, so f of x over g1 x is equals to c1, g2 x is equals to c2, and gm x is equals to cm. You can just add lambda 1, lambda 2, and lambda m, so m different Lagrange multipliers to get to do a free optimization over the Lagrangian. So now the Lagrangian would be lambda 1, lambda 2, lambda m, and then you would just do a free optimization over this thing. Yes, I hope you get the point. So this is a very important technique, and like as a machine learning practitioner, yeah, you should be comfortable with this. So any doubts in Lagrange multiplier constraint optimization? So I think with this we have done this first topic, constraint optimization. But yeah, any doubts in this thing? So I'll give you a few seconds, and if not, I'll continue with the next topic. Okay, let's go ahead then. Yeah. So the next topic is just like uh, dealing with multivariate operations on Gaussians. So this I think is like necessary because in many of the cases, as a general as a general probability distribution, if you have some random PDF and all of this is in multivariate case, uh, like calculating the product and all of yeah, doing any operations just gets messy because most of the time you have this m different integrals stacked together. But in case of Gaussians, it like so one of the major properties of Gaussians is like many a times any operations that you do on Gaussian just outputs a Gaussian, and that's like, so that's why like most of the operations on Gaussians can directly give you a closed form solution, and you don't need to apply the tricks, apply many of the tricks that we learn in Bayesian learning on where you have this good old questions. So it's you will see in probabilistic PCA as well. If you just assume that everything is Gaussian, everything comes out to be a closed form solution. That's exactly like yeah our original PCA. So I'm just writing down the formula for multivariate Gaussian. I hope you guys are already familiar with this. Yeah, mu is expectation of x and sigma. So I hope you are familiar with this already, and we can always write covariance matrix as an auto covariance matrix of x, like this is covariance of x1 x2, so x1 x1, and so I hope you guys already know this, and this is directly also equal to this thing, which is also so. I hope you are like able to draw parallels from the 1D case, and even in d-dimensional case, I think you guys are very familiar with all this, so I'm not going through it in detail. But all of this is like easier to prove. You can just like put in the definition of covariance matrix from this, and you can get these two. So yeah, this is our normal plain old d-dimensional Gaussian. And first thing that I would want is a fine property of Gaussians. This is simple. Let's say x comes from Gaussian with mu and sigma, then ax plus b also belongs to a Gaussian with a nu plus b as the mu, a sigma a transpose is the covariance matrix. A is some okay, so what would be the dimension of A? I hope this is a very simple question for you to answer. Or B also for that matter. X belongs to D dimensions. Anyone? What should A be? A vector, a scalar, a matrix?
A would be a matrix, right?
Yeah. So
And B would be a scalar kind of, you can think of, or otherwise like a vector basically of the dimension adding to each component here.
yeah. So A can be like any n cross B matrix, and n can be anything here, and B is just uh, n-dimensional vector. So yeah, AX would give you n-dimensional vector. So yeah, it's pretty simple, but yeah, it's just for you to interact. But so yeah, so A is some matrix, and then yeah, A is a matrix and B is a vector. And so yeah, so it's why this it's directly comes from our expectation of AX plus B linearity using just simply linearity of expectations. Who cares? And yeah, so for many of these things you would be familiar with the formula for 1D case, but it's better if you are also familiar with the formula in 2D cases. So everyone would know that variance of ax plus b is just a square times variance of x. But the counterpart of this would be exactly this, which I'll show. But yeah, so this, at least this would be because of linearity of expectation, and expectation of x nu is nu. So a nu plus b. And similarly, if so this would be variance, but now if I want to calculate the covariance of ax plus b, then hopefully it should give me something similar to this, which is this. Yeah. So this is kind of like in matrices, the 2 degree in 1D case, this is called, this is generally the 2 degree term, but in matrices the 2 degree term always comes out to be in this form, where something is sandwiched between the, yeah, a and a transpose. So yeah, and to prove this is just simple. Y covariance of ax plus b is a times sigma a transpose, where sigma is covariance of x. So this directly follows from using this. We know covariance of ax plus b would be expectation of ax plus b minus expectation of ax plus b. So this multiplied with the same thing, but transpose of that. Yeah, and then expectation of, we know expectation of x plus b is simply a nu plus b. So this becomes ax plus b minus a nu minus b times same thing, which is transpose. B cancels out. You can take a as common, x minus nu, and again b and b cancels out. Again we can take a as common. And we can do that because matrix operations are associative. So if you remember, AB transpose is B transpose A transpose. So this simply becomes x minus nu transpose A transpose. And A and A transpose are again constant with respect to, all of this expectation is over this, uh, of course, over x. A and B are assumed to be constant. So this becomes, and then this simply is our original sigma matrix. So this is like first property of Gaussian set. Yeah, if x comes from Gaussian, ax plus b also comes from a Gaussian with mean as a nu plus b and covariance as a sigma a transpose. So this was pretty easy. So I hope you don't have any doubts on this. The next thing I want. So yeah, please, if you have any doubts, just unmute yourself and just say it out loud. It's fine. So again, we have got this setting. And now what we are interested in is, so let's just write x as x1, x2, xm, xm plus 1, dot xt. So these are just like, I have unrolled the vector x into form of scalars, and now I'll call this component as xa and this component as xb. And so what I mean by marginal distribution is like if we know that x is comes from a Gaussian, then xa also comes from some Gaussian, as well as xb also comes from some Gaussian. So and yeah, so in so if we didn't have any PDF form of any well-defined studied form of PDF of XA, then what we would do in order to get the probability of PDF of this set of variables XA, we can just simply marginalize out the B, and then what we would get is and this thing is just simply X. So in order to prove this, we would have to solve this integral, and again, solving an integral in Bayesian set in Bayesian ML is like pretty hard because this is not just a single integral, but this m plus 1 to d different integrals stacked together, because xb is not a scalar, xb is a vector of like a d minus m dimensional vector. So yeah, so it's like d minus m integrals stacked together. So in order to get the probability distribution of xa, we would have to solve that. But since it's Gaussian, we don't need to like go through all of this. As I said, with Gaussians, most of these calculations become quite pretty easier. So intuitively, what it's like is, let's say x is just two dimensions of x1 and x2. This is x1, this is x2. The Gaussian that we have is kind of like this. So yeah, this is the Gaussian, and this is our p of x. And what p of x is just taking the first component, and the first component would be the projections on the x-axis. So if I just draw all the projections, then everything would be concentrated here. This would be sparse, and then what here the black dots represent my 2D Gaussian, whereas this would become my 1D Gaussian, and this is probability of x. This thing is probability of x, which is joint probability of x and x. So and similarly, if you take the y components, you would get probability of xp, and both of these are Gaussians. And what we are interested in finding is now again parameters of this Gaussian, which are mean and the covariance matrix respectively. So now we have x is xa and xp. So now what I would do is so okay, x is d-dimensional, x is n-dimensional, and xp is d minus n-dimensional, and obviously m is less than equal to d. So now I would split all my mean and covariance of x accordingly. So nu is expectation of x, and I would just make it nu a and nu b. And again, this term would be m dimensional, and this term would be d minus m dimensional. And similarly, my covariance matrix is sigma AA, sigma AB, sigma BA, and sigma B. So this thing is again uh, m cross m. This thing is d minus m cross d minus m. Uh, this thing would be, so sigma is d cross d dimensions. So this thing would be m cross d minus m, and this thing would be d minus m cross m. yeah, so it's I kind of like split it into all of these components where each of them is m dimension, d dimension, d minus m dimension, so that we can split x into xa and xb. So any doubts still here? Okay, seeing that, we'll move further. So this all this all is like just d dimension what we have originally. Minus t plus t. And now what we need to find is probability of this xa, and we try to use the affine transformation that we saw previously, that how and we'll multiply x with that transformation to obtain xa. And that affine transformation is just very simple. If I just uh, so x would be ax plus b, where b is a zero dimension, where b's are all zeros, and a is m cross d matrix, where so we know m is less than d. So all of this is zero. This thing is m cross m dimensional identity matrix, and this is d minus m dimension zero vector. So yeah, I hope you don't have any doubts in this. And now, if you can see, then I hope it's easier for you to identify if I just multiply ax plus b. So the multiplying identity matrix just gives us the original thing, but now we don't have this, the entire identity matrix. But what will be just kind of just removing the m part. So the first m dimensions of x would be multiplied by identity, which would result in getting us the first m dimensions, and the rest of the dimensions would be multiplied by zero. And yeah, so that would result in nothing. So this ax plus b would give us exactly x, where a is a, yeah, where a and b are defined here. So do you have any doubts? Should I like multiply the matrices and show them to you, or this is fine? Did you get this equation, everyone? Please give a thumbs up or anything. Are you all with me? I know you. Okay, I'm just going to wait until I see 4 to 5 thumbs up, or maybe just type in chat. Are any of you with me? Are you understanding what I'm trying to say? Okay, I need 2 to 3 people to respond at least.
या
Uh,
सॉरी मैं म्यूट नहीं अनम्यूट नहीं कर पा रहा था हाँ हाँ आई एम विद यू या
can you just
Okay,
scroll a bit up, like this one? And this.
yeah,
Can you just scroll up?
okay.
No, yeah, yeah.
Just tell me
No,
where
no,
to stop.
like uh, I was a bit confused about like why B is zero. Like, that means here in this case, uh, like for that affine transformation that we perform.
Oh,
So
yeah.
yeah, in this case,
So it's like we are trying. What we are trying to do here is so B doesn't need to be zero for our affine transformation. We are choosing B to be zero because what we want to do is get XA. So we want from X, we want to obtain
okay,
XA. And the way we are obtaining is choosing this
linear transformation.
A matrix that, yeah, and that linear transformation is just like affine
Yeah,
transformation is like, yeah, so B is zero, and that's linear transformation, and that's using A that would just extract out the first m columns and just so if you remember the definition of XA, It's just like the first m columns of
Mm-hmm.
the
Yeah.
vector x. So choosing in that way, that would just the identity matrix will be multiplied by this, and we would get
Yeah.
yeah, we would extract this, and all of this would just
Our
become
the
zero.
interest would be zeros. Yeah.
Yeah.
Okay. Got it.
So yeah. So if so if just to ensure this all everything else is zero, and here x1, x2 till here it's xm plus one, and then xd. So first column would be multiplied. So everything else is a zero, and what we would get out is x1, and then in the next row would give out x2, and there are m such rows here. So and remember this is m cross d dimensions. So m cross d multiplied by d dimensions just gives us m dimensional vector, and so all of these m cross rows would just extract out x1 to xm, and all of these further contributions are just zero because all of these are already all the values in this matrix are just zero. So this a extracts out yeah. So and now we proved earlier all the affine transformations results in a Gaussian directly. So now it's easier for us to see that okay, a is yeah. So x a is also a Gaussian, and then we can just use mm, yeah, we can just use this fact to obtain what our distribution of xa would look like. So we have ax plus b coming from a nu plus b times sigma. This we know b is zero, so this just goes out. And now, just as ax extracts first m of x, the a new part extracts the first m variables of new. So a new is just simply new a, and new a and new b are so if you remember this, so new a is just like first m dimensions. So it's yeah. So a new so as shown earlier, ax extracts the first m elements of vector x, and a new will extract m elements of vector new, and first m elements of vector new is just new a. And so this now we have is simply new a. And now what I want to show is a sigma inverse a transpose gives us sigma aa. So sigma aa is just this first term. So a is m cross d. This thing is d cross d, and a transpose is d cross m. So we, the output should be m cross m dimensions matrix. So if we have now a is this, these are the m's, this is zero, this entire thing is zero. Sigma aa, sigma ab, sigma ba, sigma bb. This thing is a, this thing is sigma, and writing third matrix a transpose down. So here, if I take this transpose of this entire thing would be zero. This would be my identity matrix. So first, let's say we multiply these two things, and then I hope if you are able to see this. But now only sigma a would be so sigma b a would be multiplied by this bottom zero part, and that would go to zero. Similarly, sigma bb would be multiplied by this bottom zero part, and even that would go to zero. Whereas sigma aa and sigma ab will be multiplied by this top part, which is identity, and that would retain those things. So now what we would have, so if you have any confusion, so it's just pretty basic stuff, and you can just like do it on your home once the lecture finishes. So I don't want to waste your time in that. And then this becomes sigma aa and sigma pa. And now the again, as said earlier, this would extract the first m parts of this vector, and then this would just result in sigma a. according to our matrix A, this would result in sigma A. And then simply we would have XA comes from A nu. So just finally write it mu A and sigma A. And similarly, we can also prove that XP comes from mu P and sigma. So I hope marginalization of Gaussian is clear to you. Then the next thing is conditional Gaussians. So we started with distribution of X. Then now just remember this terminology. I won't always write what each of these belong to. XA, XB, X, or X is d-dimensional vector. This thing is going to stay constant in like everything that we do now. So now we proved that probability of XA and XB are yeah. So distribution of XA is also normal. Distribution of XB is also normal. We started with distribution of X. Now we need to prove that distribution of XA given XB is also normal. So and yeah. So and all of this is like it seems pretty vague because I haven't shown you where it's useful or things like that. But just trust me on this. All of this is like quite useful, and like people would just mention it without proving it because so these are just the steps that I'm taking to prove some final thing, which is quite very messy. So and like proving this is like easy. It's not that hard, but it's just like too lengthy and stuff. So yeah, so now what we are interested in getting the probability distribution of XA given XB. So I'm introducing a new variable here. This is called a precision matrix, and precision matrix is simply the inverse of a covariance matrix. And dealing with precision matrix is easier because in a formula of Gaussian, we have so, yeah, we have inverse of our covariance matrix. So yeah, so dealing with precision matrix is many a times easier than dealing with covariance matrix. And so precision matrix is simply sigma AA. So again, draw parallels to covariance matrix. All everything is the same. And now, yeah, can anyone tell me if this holds true? Hmm? Anyone? I know this holds true, and obviously sigma is sigma AA, sigma EB. So it's like just like dividing the matrix into four different components. So I can write like four different equations here, and yeah, will it hold true? Will it not hold true? If yes, if not, provide reasons. Just a random guess, maybe someone. Okay. Anyone?
Will it not hold true because of the minus sign? No, I'm just guessing.
Minus sign as in. So this is the inverse, right? Yeah. So
Yeah.
so what do you mean by minus sign? This is just like the inverse of the matrix.
Yeah, so in the adjacent matrix, there would be like the sign would change, right? So because of that, would it be a problem in the equality condition?
Yeah. So it would be a problem, but not necessarily because of the minus sign. So,
Like due to inverse sort of like the first thing is sort of in this case whether the inverse exists. So maybe like based on that it would be an issue like so if there's no inverse.
sorry, what?
But
Can you repeat again?
since here like we are basically taking the inverse of that particular covariance matrix, so like I'm not sure like if this is right, but like first thing is like whether the inverse exists for this particular covariance matrix,
Hmm.
and then based on that like we are basically dividing it into components. So here like this A would not like exactly map to this sigma like inverse of A like right because there would be swap of values like if we take inverse to the like sort of a inverse in a way let's say means exactly
Yeah, yeah. So you are true. So this so because so one way to show that would be simply like if I write it in this way, and I know this, then I would want sigma inverse to be I, and I know sigma is uh, yeah, sigma is sigma AA, sigma AB, sigma BA, sigma BB, and sigma inverse is mu AA inverse, mu AB inverse, mu BA inverse, and mu BB inverse. Yeah, and if I just multiply these things, and I like I hope you know why we can multiply these things together, and like why the way we multiply matrices. These are not the elements of matrices, but these are sub matrices within the matrix, but still we can multiply them. So like just in your head, be clear about for every operation that we are performing and whether we can perform that operation or not. If you think we cannot, then please just interrupt me. And it's like pretty easy to show that if you even multiply the element wise matrices together, the subcomponent of the matrix corresponds to just multiplying the two corresponding components of this matrices. So if we choose, yeah, so this, yeah, this thing would become my AB inverse. So, oh my God, sorry, because of the lack of space. But as you can see, there are like directly there is combinations of this term coming here, and then now simply if we just look at this first term, we know this would go to our, if we choose our sigma AA to be, I don't know why I'm calling this sigma, just I'll call this caret. So okay, precision. I don't know what the technical term for this thing is, but yeah, the precision matrix of AA, and if we multiply this, then we would know this becomes I. But then there is also this additional term, and there would be such additional remnants in each of the term, and so so this thing sigma AA inverse should be should include this term as well as this term. So we'll see later what sigma again sorry what precision of AA turns out to be, but yeah, so but as we can see, this does not hold true. This thing is wrong. We cannot just like simply write this as this sign was. That's wrong. But yeah, so now we are interested, as I said, we are interested in this, and intuitively what this means is, again, let's say if we have this conditional uh, joint distribution just with two variables x1 x2, just before this is our 2D Gaussian. And now when I say p of x1 given x2 is, if I just simply draw a line, then what I would have is I have given you some value of x2. X2 is given, and then the x1 components, all of these. So everything that lies on this line is also a Gaussian. all the data points p of x1 given x2, all the data points just that lie on this line are Gaussians. So form a Gaussian, obviously 1D Gaussian. So just take only the points that lie on this line and take their x1 component, and you would get a Gaussian. So again, intuitively it makes sense, but we want what the mean and variance of this Gaussian is. So for Gaussians, why it's easier is again three straw parallels to 1D case. The thing that makes Gaussian a Gaussian is the exponential term, because that's where formula of Gaussian. Yeah. So yeah, yeah. So if the only thing that depends, Gaussian is always defined on this random variable x, and the only thing that depends on that x is this term. So if I have my exponential term behaving in this way, then I know it's a Gaussian for sure. I don't care about this normalization term. I just, because normalization term does not have any interactions with x. It's just a constant just to ensure that PDF integrates to one. But in order to prove that okay, x follows a Gaussian distribution, it suffices to show that the exponential term is of this form. And similarly, in 1D case, it suffices to show that the exponential term is a 2-degree polynomial. It's just a quadratic equation. And yeah, I hope you uh, have seen that before. So in order to say, okay, this variable follows a Gaussian distribution, we just care about what the exponential term is. So that's what we are going to do, and that component is also, I think, called what. So first of all, we are interested in this thing. I want my exponential term to behave in this way, and uh, this this root of this is called Mahapulis distance or something. This is the criteria, but yeah, it doesn't matter. So this we are interested in in knowing that the exponential term of xa given xb should follow that. So now we have probability of x is equals to probability of joint probability of xa xb. Follows this. And now I'll just expand each of this. So exponential term of this thing would be minus half x minus nu transpose sigma inverse x minus nu. So this we are working in the t-dimensional case on our original vector x, which we know to be, which we know that it's a Gaussian, and we know the values of nu and covariance matrix sigma. So now I'll unroll this to get our sub vectors xa, nu, b, and all of that. So xa minus nu a, xb minus nu b transpose. And now, as I said, why dealing with precision matrix is easy is because now I can write this at least, because sigma inverse is just precision, sigma inverse is equal to precision matrix. And then again, I have the same thing. Now we know that while so this is the formula of x, but now we know sorry, distribution of, not entirely the distribution, but the thing that matters, exponential term of our x, probability of x, which we know is a Gaussian. But now we know that we are given the values of xb. Xb is given to us, and we are interested in showing that the xa also follows, has a similar exponential term. Like if I just say, okay, xb is given to you, then but the this component in terms of variable xa also follows the same pattern. So if we just unroll this, then It's just like I'm unrolling each of this component out. So xa minus this thing gets multiplied to this thing, which gets multiplied to this thing, and then this thing gets also multiplied to this. So it's just like unrolling stuff out and like so as previously said, nothing in this is like difficult. It's just too cumbersome. So now this thing, so it's a transpose. So like this thing, imagine it as xa minus mu. It's a row vector. So this is what it turns out to be if you just unroll everything. And now we would assume that in this xb is given to us, new b is given to us. We are just interested. Yeah. So for xa we would just treat x as a constant, and then we would rearrange all of these and try to write it in terms of xa because we just need to show that the xa and all of this is in just in the exponential term, and we just need to show if we are given xb, then the exponential in terms of xa, the exponential term follows a similar function. So and I'll just digress a bit because I just need to kind of show you this thing. And so once we have this exponential term, the thing it equates to is, so in the exponential term we know it's minus half x minus nu, minus x minus nu, and if we just again open all of this stuff up, what we get is minus half x transpose sigma inverse x minus x transpose sigma inverse nu minus nu transpose sigma inverse x transpose plus nu transpose. And now again, this is a constant. Only these three terms depend on x. X transpose sigma inverse x. So yeah, you can simply add this because this thing, if you have seen previously, you should know that this thing evaluates to a scalar value because this is d cross d, nu is d cross 1, and x transpose is 1 cross d. So it just gives you a scalar value, and because since it's a scalar value, you can take its transpose. A transpose A is A because it's simply a scalar, and if you just take this transpose and you get this. So, these and these are essentially the same. So what I wanted to say is you can, if you have this form, you can just directly extract out the sigma inverse. Sigma inverse is simply the coefficient of the 2-degree term x transpose x, and you can also extract the new term, which is just again the coefficient is x transpose sigma inverse. So the coefficient of second order term is sigma inverse, and coefficient of your first order term is sigma inverse nu. So you can directly extract out sigma and nu from just the exponential term in which we are dealing. So yeah, back to this part where we were. So now we have unrolled this, and we just want to see in terms of xa what the equation is, and treating everything else as constant because we need to see how xa interacts, yeah, in the exponential term. So it just simply turns out that if you so the only 2-degree term that we would have is xa sigma aa and xa. So that's the only 2-degree term that we are going to have. And then the 1-degree term, which would be just simply in terms of xa, is when nu a would be multiplied to xa, and again this nu a would be multiplied to this xa, and this xa would be multiplied to this term. and this xa would be multiplied to this term, and this is constant with respect to x. So just multiplying all of this together, what we would get is sigma a minus sigma ab times xp minus ab, and everything else is just constant. So yeah, I'll just write plus c. And now, if we compare the second order term, we know this is in terms of xa, and again we got what we wanted. So it's the exponential term behaves in this manner, and hence we know it's a Gaussian. And if we just like directly by comparing stuff, we know sigma AA um, becomes our covariance matrix of sigma A given B. So A given B inverse becomes this precision matrix AA because so from this to this what we have done is assume that B was given to us, and hence everything is like conditioned on A given B. And that's why we can just treat all of the xb terms as just constant. Even here, xb minus nu b is just a constant because we are just essentially interested in dealing with the interactions of xa term. And the mean of a given b is this entire thing. Okay, no, sorry. So we take the transpose, this transpose, and then sigma inverse nu is this entire thing. So sigma a given b inverse nu ab is simply the same sigma precision A nu A minus sigma AB xp minus nu p. Then we'll just multiply and this thing. Okay, we know precision of AA. We just multiply both with inverse of that, and then what this would just give us identity matrix, and this would nu A inverse AB times xp minus nu p. So and this is the linear, yeah, this is the mean of our x given xp. But now what we want, okay, so we want to know what sigma AA inverse is, sigma AA is, and we have no clue about that, right? Because we know that this doesn't hold. So what each of the individual components in the precision matrices are. And so I would just state what each of them are, and we can just verify it. Uh, so, and again, this is like used multiple times in many of the linear algebra. So if I have some matrix A, B, C, D, and if I take its inverse, because that's what we are essentially doing, right? We would have M minus D plus. So yeah, no one expects you to remember this. It's just like too messy. M D inverse D inverse plus D inverse C M B D inverse. So maybe I should write that in a better way. D inverse C M minus M B D inverse where M is A minus B D inverse C. It's called Schur's component. So it's like just uh, as we thought, it wouldn't be as simple as just A inverse here, which is not equal to A inverse. It's yeah, and we can easily verify it. If you want, I can just verify the first part for you. So the thing we would get in the top left part is AM. So what I'm essentially doing is just multiplying this inverse with ABCD. So ABCD inverse with ABCD to show that the first thing literally evaluates to identity. So we Yeah, and we know this thing equals to this messy thing that we have here. So the top left component is just m times a plus okay minus m d inverse times c. I hope that's right. Yeah. So now we know m is mm, okay. So m is this messy thing here. So then this becomes a minus b d inverse c inverse. Mm, okay. Yeah. So this thing, and then we have to multiply that with a minus. Am I missing something here? Yeah, and then this thing becomes okay, a minus b d inverse c times yeah b d inverse c. So we can sorry, this is here inverse here, and then we can just take a minus b d inverse c minus 1 as common, and then this simply becomes again a minus b d inverse c, and then hence the value is identity. So I won't go through each of these. Just I did for the first one. Maybe you can try for the second, and you can verify that if you multiply now if you multiply this we got for top left corner if we get for top right and for bottom left it should evaluate to 0 and again bottom right should evaluate to identity matrix. So you can verify that all in your free time, but that's what you get for this stress component. And then you can just simply we can then now we can get sigma a inverse in terms of precision a inverse in terms of all this. And what it simply becomes is so a given b, we know it came out to be this part, and then simply just using the fact that so the way you would see so it simply becomes m here the sigma a so if just showing parallels with the way we divided up original thing. This is sigma a, and then if I'm taking in this thing represents my new, so my m represents new a, and we know that m is simply a minus b d inverse c. So if I just substitute a as sigma a, b as sigma ab, then it turns out that what I get is sigma a minus sigma ab times sigma bb inverse times sigma ba. So and because sigma a is just m inverse, and again inverse of that, it's just which is just basically m, and m is a stress component, which is a minus b d inverse c, and this is a, this is b, this is d, this is c. So if we are given b, then sigma a given b is sigma a minus sigma a b, and then new a given b is simply new a. Now, yeah, now we know what sigma a inverse is, and we also know what sigma ab is. So we can simply substitute our again. I'm sorry, I'm saying the precision matrix of sigma, but yeah, so we can substitute those values there, and what we would obtain is this. And then we know xa, xp follows a normal distribution, and xa with mu a given p This is our conditional distribution. Any doubts in this? I know that it's a bit heavy on maths, and I didn't like go over the substitution for new, but you can, because it would just like involve a lot of terms, but it's all simple maths that you can do yourself. So any doubts in here? I think it's a bit heavy on maths. I wanted to do also Bayesian theorem for Gaussian variables, but I think should I hold it or should I continue? And most of this is in I think third or fourth chapter of Bishop, so you can just like refer to that as well. And if you want, I can just like I've solved all of these equations, and if you want, I'll just add this. Uh, I'll scan the notes and just upload it on Drive, so you can work it out all of these equations and all of this stuff for yourself. But yeah, should I continue or it's a bit overwhelming and I should just stop, please? Anyone? Okay. Okay. So we are tied on 1-1. But at least I hope that you understood all of this. So please just like unmute yourself. Any doubt, give me feedback, or just give anyone. Okay, yeah, anyone either give me a feedback or give a summary of what we have done, and also say should we continue or should we just stop? Please, I'll start with a random person and tag someone else. Either a feedback, either a summary, or yeah, just say anything.
Hello, Fenner.
Yeah.
Yeah. So this is all understandable, like everything. But would it be possible to make this a bit interactive? Like if we do some coding based on this. So because for the research session, we have the presentation of a Bayesian paper, the paper based on Edward only. That is the library. So, and we were finding it a bit difficult to, map concepts to the code that we have done completely. So, would it be possible to integrate some more coding practices or something like that, like working on a basic problem?
Yeah. So I saw your slides, and like it was the variational inference and the things that you were going to say. So in so if we had continued with EM algorithm today, I wanted to like so obviously this is all just theory. I don't think we can do any much interaction here. It's just like what each of the thing comes out to be. But we can. This is simply maths. But in the Bayesian session we have, I think yeah, it would be better if we can just try with some EM algorithm on GMM or something on data set, and also show how variational inference works. So I'm not familiar with Edward, but yeah, I think it's definitely a good idea, and we should try that. So
Yeah,
if
I mean,
in
not just Edward, but any framework would be fine.
Yeah, yeah. Means I think
yeah
Swapnil was going to give a session on probabilistic programming next week, so probably that time maybe we could have this thing and like kind of we could also
Yes,
try
we
to
are still on for that.
yeah like so like after that session we could try and like sort of present some demos or something like that, with workable demos of like whatever we have learned so far. Like that would be a good exercise for us as well, like, and we could interact and like in the channel and kind of clear our doubts as well like that too. It will be more better like if we try to apply first from ourselves and like let's see like if we don't
Actually,
get
I
anything
just
like
submitted a paper about COVID modeling with Pyro. So
okay.
things like that are super, well, I won't say easy, but straightforward to do with these frameworks. So I would definitely like mini projects to that end that solve like problems. I should stop recording though if we are done.
Yeah, I think
so yeah I'm not sure. So yeah, people please just, I don't mind continuing, but I can understand if it's a bit overwhelming, and if we want to like switch it to the next review session. And also, yeah, about the programming part. Once we switch back to EM, and I think, yeah, once you are completed with EM, like applying EM and additional inference and all of these via code and by programming, yeah, I think it would be better to nail the concepts. So, but yeah, on this part, yeah, please, at least make it interactive verbally so that we can, yeah, I get to know if it's better, if you are, if should I go ahead further or anything like that.
In terms of programming, the Coursera module has like programming questions. So I think either we can solve it in our time, or you can go through the programming as you go through this theory. That might help.
Yeah. So that course uses PIM-C3, if I recollect correctly. Yeah. So, yeah, even PIM-C3 is a great library for doing all of these variations of Bayesian inference. But yeah, like it's I don't, so that was a course I did a while back, and I don't remember exactly the questions and how to use that library right now. So for me, anything is the same, like PIM-C3 or Pyro or Edward, like anything that people are comfortable with, you can use that.
And like I would prefer basically sort of a small some application demo or something which have this math involved in a way, so it explains kind of in a way like the simulation in a way like kind of how the abstraction of this concepts are abstract concepts are used in like this is a particular, let's say, for this applications, and like basically like how changing this sort of what I mean, this different parameters or like that way how it affects sort of, so it kind of helps a bit like to reinforce like the concepts as well, like sort of, and get more better understanding about the topic as well, like something like
I
that I think of.
Yeah, so I think we can talk about it once we stop the recording. So, but just maybe if on this lecture, if we should continue or just stop it, if you can just give some feedback or just like cover what what we had in this lecture, and then we can just stop the recording and move to talking about programming and stuff. So yeah, uh, anything related to this, just please unmute. Please give us summary feedback or yeah. No one told me like should I continue or should I stop, and I think that's an indication for me to stop.
So like I understood the concepts like in a way, but like I will have to go through like a bit derivation for the last part like that got presented, like sort of. So that is like one thing, and yeah, and probably like because we have like sort of like another session as well, like sort of that way. So it gets bit like if we have this session bit early like that way, sort of, then it would be better like what I mean. Maybe like if it's possible for you.
I didn't understand the last part. Sorry.
Last part I'm saying is sort of a like since we have like another session as well like after this sort of, so if we like have the session early or like sort of have a bit of break in between sort of like that would be better like in India it's sort of like a dinner time and sort of like that way for some of them, so me
Yeah,
as
yeah.
well.
That
So yeah, that's the thing, but otherwise yeah,
okay. So
मतलब,
yeah,
yeah,
then it makes sense for me to stop right now. The next session is at 11, right? Or 11:30 maybe.
9 o'clock I think IST, and
Ah,
after an
I
hour
mean,
like
okay, yeah, yeah.
after an hour sort of, so.
Okay. Anyways, I think I'm like randomly my screen is stopping sharing. So, the nature is telling me to stop. I don't know why. So yeah, I think we can just stop the recording.